All right, we are back, and just want to tell everyone in the second class that there was a single technical glitch in the first class, so there's going to be more students here in today's. The ones that can attend 11:30 are going to be attending 11:30. For those who were in the 10:30 class, you noticed that, like I said, it wasn't working. I literally spent the last hour completely cleaning my computer, running a number of cleaners on it, only for none of it to work. And then I looked down and I'm like, the only thing I changed is the USB cable. Could that be the problem? So I put in the old USB cable and everything works like a dream. So the USB cable in question now is a little bit broken, more broken than it was before. So we're good. I'm back. Computer's clean. And as I mentioned to my first class that, come here and, use the chat. So for the second class, those rowdy people from the first class that always use the chat, well, some of them are clearly here and are definitely going to be monopolizing the chat. So anyway, we're good. I'm feeling a lot better about it because I actually have something that's going to work and I can record this. Yes, you almost saw me an hour ago, Wilhelmina, but just can't get enough of the class. I understand that. Let's focus. Let me focus. You guys can do whatever you want in the chat. And a couple things that I did need to talk about. One of them was the presentations. And the presentations are going really well. Yesterday was a long day for me. There was 12 hours of presentations. But I sat through them and enjoyed them, which was really good. If you want to attend them, even just to see what people are doing and how people are presenting, you're more than welcome to sign in and attend. And we had a bunch of people popping in and out yesterday. So feel free to do that and just to get a feel for what else is going on in the world of science, but also how people are presenting their materials. So that was good. The other thing, I should really stop reading the chat, that I need to talk to you about is the final exam. Apparently some people do not have this in their notifications, others do, but the final exam for Chem 101 is on the 24th of April. It is a Saturday, yes I know, from 1:30 to 4:30 in the afternoon. So that is the time you need to block off for your final exam for Chem 101. Good. So that is where we are at in terms of the course material. And all right, ignore the chat. Just got to remind myself to ignore the chat. So last day we were looking at Gibbs free energy calculations, and the last thing we did was explain that because delta G is a function of temperature, the best way to calculate it is to use delta H and delta S in the equation that is at the bottom down here, because those parameters, enthalpy and entropy, are not really temperature dependent, but you can calculate delta G, which is definitely a function of temperature. So what we're going to be doing for today and Friday is finishing off the thermodynamics unit, and that is literally just a bunch of examples. So this is what we are going to be doing in terms of this example. Looking at this reaction, we're going to determine the standard reaction-free energy at two different temperatures, plot the reaction-free energy as a function of temperature, and determine the temperature when the standard reaction-free energy equals 0. So a lot of our time is going to be spent on the document camera for the next few days. So the other thing that you're going to see is you're going to see, hold on, I'm running into a problem. Okay, everything's working. Tell me you have audio. That's the only thing I need to know.
Yeah.
You have audio? Okay. Things are different somehow, and I don't know why it's not showing up for me in terms of your audio. Weird. Okay, as long as you've got audio, I don't care. All right. So the other thing that you're going to see is, again, how I set up and solve these problems. So the reaction that we're working with is that of presented there. And in order to calculate the reaction enthalpy and entropy, I'm just going to use this as a data table. And so I'm going to tabulate the enthalpies of formation and the standard entropies, and all of this comes off of the data sheet. So just going to give you the numbers. 90.3, oxygen is an element in its standard state, so it's 0. 33.2. Got that. And there's the units there. Last day we went through the calculation, so I'm just going to give you the values. Negative 114.2 kilojoules. And the reaction entropy is negative 146.5 joules per Kelvin. So we need that information, and in part A, we were asked to calculate the free energy at 2 different temperatures. And so that's simply delta H minus T delta S for the reaction. And so at 298 Kelvin, we're going to get a value of negative 70.5 kilojoules. And at 350 Kelvin, we get a value of negative 62.9 kilojoules, just plugging in those values and the 2 different temperatures as presented there. Part B asks us to plot the standard reaction free energy as a function of temperature. This doesn't need to be some amazingly great plot. It's ultimately to figure out when it is spontaneous. And so if we were to have a graph that looks like this, where we have free energy as a function of temperature, what I would like from you, oh no, I'll get to that in a second. What I would like to do now is to sit there and look at this expression and realize that we have the equation and at 0 Kelvin, delta G equals delta H at 0 Kelvin. So at 0 Kelvin, we calculated it as negative 114.2. So our first value would be somewhere down here, negative 114.2 kilojoules. And given that delta S is negative 145, is this slope upwards or downwards? Do I have a positive slope or do I have a negative slope? I got people going upwards, negative, positive. Remember, we've got a negative sign right there. So that means that when we have delta S is negative, the entire thing is actually positive, and you have something that looks like that. So you end up with a positive slope. We'll get back to this graph in a little bit as we do part C, because right now, the other thing we want to do is find out what that point is right there. When does delta G equal 0? Part C asks, determine the temperature when the reaction free energy equals 0. So we have the equation that we keep using. When we set it equal to 0, we have delta H is equal to T delta S, or the equation that we used previously, T is equal to delta H over delta S. And I would like you to calculate when the temperature equals, or what the temperature is when delta G is equal to 0. So you have the values already in your notes. What is this temperature? I would highly recommend that you put units into your calculations. You actually put units into your calculations from the very beginning. There we go. Really? JK? Uh-huh. If you look at the units that we have in our values, it is kilojoules and joules. So there's a factor of 1,000 that you need to incorporate into your calculation. So, and when you do that, you get what everyone else is getting to 3 significant digits. You get 780 Kelvin. So this value in the graph is 780 Kelvin. And so this reaction is spontaneous just by looking at the graph at low temperatures. And that's it. Good deal. Does anyone have any questions on that? Looks good. All right. So that is these calculations. So that's the basics of these calculations. Now they're going to start looking at some nuances. What does it mean to be under standard conditions? When we were doing these calculations, we have this idea of standard state. So there is a difference between delta G versus delta G naught, just like delta H versus delta H, standard conditions. Anyone happen to know that refers to standard conditions? Anyone happen to know what those standard conditions are? It's in the next page of your notes. Or it might not be. You might not have it written down. It's not 25 degrees Celsius. That's about the only thing that's not done. We're dealing with 1 mole per liter solution, 1 bar pressure for gases, okay, and that's it. The important thing is that temperature is not specified. Okay, under standard conditions, this isn't standard temperature and pressure or standard ambient temperature and pressure. This is thermodynamics standard conditions, and they refer specifically to 1 mole per liter solutions and 1 bar pressure, or more formally, unit activity for the solution and the pressure, which we've assumed to be 1 bar and 1 mole per liter. So in all of the previous slides, anything without the degree symbol means that they're valid under any conditions. So I'm not going to go through the derivation of it, but we can calculate the free energy under non-standard conditions. Why? Because life exists under non-standard conditions. The atmosphere contains 21% oxygen. So the atmospheric pressure, partial pressure of oxygen in the atmosphere is about 0.21 bar. You look inside your human body, you're not at a pH of 1 mole per liter, or 1 mole per liter hydrogen ion, or a pH of 0. You have a biological pH of around 7.3. Life doesn't exist under standard conditions, and we need to be able to calculate what the free energy is under the conditions that we're actually operating at. And that's where this expression comes in. The free energy calculated under non-standard conditions is calculated as free energy non-standard is free energy standard condition plus RT ln Q, where Q we defined in the equilibria unit as the reaction quotient. And that was wherever you happen to be, what is products over reactants for the state as it currently exists. We're going to see in a little bit that that relationship links thermodynamics and equilibria, so we'll actually be able to calculate equilibrium constants very quickly. But to emphasize what this is, delta G, under standard conditions, delta G, sometimes called, I'll use it as naught, delta G naught, refers to a reaction occurring under standard conditions, and delta G without the degree symbol refers to a reaction occurring under arbitrary conditions, just happens to be whatever. The one thing I want to point out, and this is completely as an aside, but if you happen to be carrying on in chemistry or physics, you're going to see two things. The standard conditions could be written like that, or they could be written with that symbol there. And whether it is a degree symbol or the one on the bottom happens to be called plimsoll, no big deal. The real difference between the two is that versus that, the one on the top is used in North America, and then the one on the bottom is used in Europe. You think these scientists would get together and agree on one? No, they didn't. So I have opened chemistry textbooks, and the first words out of my mouth was, oh, the author's European, just because I happened to see what the standard condition symbol actually is. So thought it might be kind of humorous to you, but it's there. All right. What are we going to do with this? We're going to apply it. So in this example, we have non-standard conditions for ethene and ethanol, and we're going to figure out, is this reaction spontaneous under these non-standard conditions? So to rewrite the reaction, that is the reaction of ethene plus water vapor to form ethanol. And everything's going to, just like equilibria, everything's going to start off the same. We need to calculate the standard enthalpy and entropy of reaction. So all of these data values come off the data sheet again. And so we have that. Those are the tabulated formation enthalpies and standard entropies. I would like you to go through and calculate what delta H and delta S of reaction are, as well as calculate delta G at 373 Kelvin, which is the temperature that we're operating at. So once you get delta H and delta S, please type those into the chat, and then everyone can move forward and calculate delta G at 373 Kelvin. I get a different enthalpy. I could be wrong, but I get a different value, Abigail. All those negative signs make things confusing. So we're a choice between 45.4 and negative 45.4. We'll go with the negative 45.4 kilojoules. Good. How about delta S for the reaction? We're going to go with, negative 126.5 joules per Kelvin. Good. And now you can take those values and calculate delta G at 373 Kelvin. Good job, everybody. I don't need a temperature. I'm looking for what delta G is, not when it's equal to 0. But you got the right value. That is when it crosses from being non-spontaneous to spontaneous. Kenzie got 1,1784. Right. If you are going to convert it, you're going to get 1,780 something units. So, or I'm just going to go with 1.78 kilojoules because we are limited to the units decimal place on the kilojoules. So because you're limited to one decimal place in the addition and subtraction process here, we are actually limited to one decimal place down in our final answer. Remember, this is an addition subtraction thing. The other thing we want to point out is that being positive, this is not spontaneous. Under standard conditions. Not spontaneous under standard conditions. But we're not operating under standard conditions. We have different conditions, and so the relationship that we're going to use is the one that was given earlier. And if you go and look at the equation, you find that Q, all of the things are gases, will be the pressure of methanol over the pressure of ethene, H4, times the pressure of water, because it's a gas. All right. So it's going to come up in just a second that there's going to be a unit glitch, and I'll explain what happens to that in just a few seconds, but we'll go with that. So if I plug numbers in, I have 1.78 kilojoules plus a value of 8.314 joules per mole Kelvin times 373 Kelvin times the natural log, and to put values in, we have 2.4 bar over 4.8 bar times 1 bar. Now, in terms of units, Kelvin is going to cancel, but this mole down here isn't. And the reason for that is that up here, we don't ever include the N in the reaction. It is 1 mole of reaction. So there is an implicit N is equal to 1. And if you remember the equation PV equals nRT, well, in the derivation of this, you have nRT, but N is always equal to 1. And so that's going to address that issue there. So the other one in terms of units is that this must be in standard units. And we've defined standard units as 1 bar partial pressure for gases. So that is the condition in which all the thermodynamic data is tabulated, is in bar. So the units of bar need to be in that equation there, or else it's not going to work. When you do this calculation, reminding that you have kilojoules and joules, what do you get as a value for delta G again? That will come back, I hope. There it goes. Anyone who was able to calculate delta G here? 2 people got the same value. Do you have units on that? Three people got the same value. Your number's right, and your units are joules. To put it into kilojoules, it is negative 0.37 kilojoules. Again, because of the addition subtraction, you're limited to 1 decimal place on the units. So negative 0.37 kilojoules. The negative tells us that it is spontaneous under the experimental conditions. Spontaneous under experimental conditions. And that's what we wanted to show. We wanted to know what the spontaneity was under the experimental conditions. What we found was that under the standard conditions, it was not spontaneous. But when the conditions were varied, we have found that the process is spontaneous under standard conditions. What questions do you have on this? Anyone? Give you about 20 seconds if you have any questions. Okay. If you do have questions, just, it's a slightly esoteric concept, a little bit, lots of math, lots of unit aspects associated with it. If you do have any questions, feel free to contact me or the TAs to discuss it. But that's how these calculations are done. Now we're working under non-standard conditions. We're able to calculate the spontaneity, delta G of the reaction, under those conditions. What I want to do is now start looking at what does it mean for something to be spontaneous. And we're going to start by deriving an expression that relates the thermodynamics to the equilibrium constant K. And so the equation that we have give me a second here, RT ln Q. What do we know about being at equilibrium? What do we have? At equilibrium, what can we say? Things about equilibria, things about thermodynamic values. Anyone remember something about it from the equilibria unit or from what we were just talking about in terms of free energy? Good, excellent. At equilibrium, Q is equal to K. That's good. How about free energy? What can we say about free energy when we exist at equilibrium? Delta G is equal to 0. It has to be very specific because equilibrium exists when we're not under standard conditions. Okay, delta G non-standard is equal to 0 at equilibrium. And so we're going to take these values and we're going to substitute them up there into that equation. And what we get is that 0 is equal to delta G naught plus RT ln K. Or more commonly written is that delta G naught is minus RT ln K. This is the link between thermodynamics and equilibria, or another way of writing it. So now what we're going to look at is what does it mean to be spontaneous? What is that? Oh, ignore that. Well, we're going to not ignore it, but the chapter numbers probably don't apply to what you took, but let's just look at the progression that we had in Chem 100 and Chem 101. When you looked at electrons and how those electrons distribute themselves in orbitals, if you did a little bit of that in Chem 100, what you found is that electrons arrange themselves to minimize the electron repulsion. So they put themselves into orbitals, they arrange themselves in 3D space to minimize the electron-electron repulsion. That reduces the energy. Minimum repulsion is a minimum energy. When you formed chemical bonds, okay, chemical bonds formed because you had a lower energy. Energy was released when you formed the chemical bond, and so it was more stable. In order to break the chemical bond, you needed to put energy in to break that chemical bond. And what we look at here in this chapter is we're looking to say that, gee, chemical reactions are going to minimize the energy of the system. The energy that we're minimizing is actually that of the free energy. The free energy is minimized to give us the most stable state. So what does that mean in terms of thermodynamics and equilibria? Well, delta G naught, delta G standard conditions, pertains to the equilibrium constant. It gives us information on the equilibrium constant. If delta G naught is less than 0, that is, the reaction is spontaneous, K is greater than 1. The equilibrium constant is greater than 1, saying that the products are favored in reaction. If delta G naught is greater than 0, okay, and we said that that was a non-spontaneous process, K is less than 1, and the reactants are favored at equilibrium. And in the rare occasion that delta G naught is equal to 0, then the equilibrium constant is equal to 1. If we go back over to here, if you remember from the equilibria unit, I gave you this expression that said the equilibrium constant ranges from 0 to 1 to infinity, where 1 was the midpoint. Here, we had the reactants favored, and over here, not that I can draw, products are favored. But the other thing was that the midpoint in this equilibrium expression was 1. We come to that same conclusion now in the thermodynamics unit, where 1 is the midpoint. Delta G, standard conditions equals 0, equilibrium is 1. Delta G is less than 0, equilibrium constant is greater than 1, products are favored. Delta G is greater than 0, non-spontaneous, equilibrium constant is less than 1. That is what delta G standard condition, delta G naught, tells you. When you look under the non-standard delta G is a function of temperature, it pertains to the state of the system as it is under those conditions. If delta G is less than 0, the forward reaction is spontaneous. It's going to move to the right to reach equilibrium. If delta G is greater than 0, it's going to go in the reverse direction in order to reach equilibrium. And if you happen to be having delta G equal to 0, you have a system that is at equilibrium. So delta G naught tells us where the equilibrium position is, while delta G non-standard tells us what direction we need to move in order to reach equilibrium. If you're more comfortable visualizing this graphically, this is a graphical representation of this, where on this figure what is plotted is the standard free energy. Okay, standard free energy, delta G, or G naught, as a function of the extent of reaction. On the left-hand side, you have all reactants. On the right-hand side, you have all products. So that's the extent of reaction, reactants to products. And what it really is indirectly telling you, if you've taken calculus, you'll note that delta G on both of these conditions is actually the slope of the line. And here the slope of the line is positive, which means the reaction is going to go in that direction to reach equilibrium. Here the slope of the line is negative, and the reaction is going to go in that direction, the forward direction, to reach equilibrium. At some point there's going to be a minimum, and that is the equilibrium position right there between where you have a minimum in the figure. Before I leave this picture, does anyone have any questions on it? All right, I do have one more thing to point out. And the one more thing I have to point out is the magnitude of delta G naught. Here we have delta G naught is large, and I'm just going to roughly badly type large. Whether it's large positive or large negative, it doesn't really matter. Here, the equilibrium position is all at reactants. When delta G naught is a large value, the equilibrium position is all at reactants. Here, it's a large value as well. It just happens to be large negative. And the equilibrium position is all products. When delta G naught is small, the equilibrium is somewhere between the reactants and products. One of the things that is a misconception sometimes taught to students is that, quote, everything's in equilibrium, everything's in equilibrium. That's actually not the case. There are values of delta G that are so large in magnitude that the reaction goes all the way to completion. It's a complete reaction, or so large in the positive side that it doesn't actually react. And sorry, I'm going to go to this slide, then we'll come back and we'll do this in an example. So I'll go back and do the example in just a few seconds. Equilibrium implies that some reactant and some product exist at equilibrium. You need to be able to do something to shift the reaction. So when you're at equilibrium, you have some reactant and some product. Okay, a complete reaction is the condition where every molecule of the limiting reagent is used up. Furthermore, a non-reaction doesn't produce one molecule of product. And it is actually possible to go through and calculate the value of delta G where you literally either go to completion or you don't have one molecule product being formed. It does depend on the stoichiometry, but as a general guideline, if your delta G naught is beyond plus or minus 400, you do not have a system that reaches equilibrium. Okay? If it's less than negative 400 kilojoules, the reaction is going to proceed to completion. If it is greater than plus 400 kilojoules, you have a situation where no reaction actually occurs. And we are going to finish off by calculating delta G and the hypothetical equilibrium constant for the hydrogen-oxygen reaction. And that was this one right here. Assuming that the combustion is an equilibrium process, determine the equilibrium constant for the hydrogen combustion at 298 Kelvin. We're forming liquid water at 298 Kelvin. So we have the reaction elements in their standard state have a formation enthalpy of 0. For liquid water, it's negative 285.8 kilojoules per mole. We actually have time. We'll finish off with this example. So I would like you, now just in terms of this, remember you've got stoichiometric coefficients that you need to worry about. Go through and calculate delta H of reaction, delta S of reaction, and delta G at 298 Kelvin. Once you get the values, just type them into the chat and I will add them to the tablet. Correct for delta H, negative 571.6 kilojoules. Someone else for delta S? $326.7. Brianna's not too sure about that one. Do other people get the same value or do they get a different value? Now we now have 3 different values for things. Brianna was actually correct. It's negative 326.7 joules per Kelvin. Brianna. Why are you thanking God? You should thank yourself and your calculator. You're good. You did good. What is delta G naught at 298 Kelvin? And my skills are her skills. Don't answer that, Alex. Okay, good answer. While you're typing, other people are plugging numbers into their calculator, making sure they've got the right units. What do you get for delta G naught? I think you forgot to convert between joules and kilojoules, Abigail. And yes, Benjamin and others are getting negative 474. Somehow things are moving. Negative 474.2 kilojoules. All right, negative 474.2 kilojoules is the value. I'm just going to finish this off. I'll go back and talk about that number in just a second. In order to calculate the equilibrium constant, we can calculate the equilibrium constant for anything, is equal to minus RT natural log of K. And if we want the equilibrium constant, K would be equal to E to the negative delta G naught over RT. So here, when you plug values in, you get as an equilibrium constant the value of 1.33 times 10 to the 83. And because we've set our units as bar for all of these calculations, and the units just, here there's magic. I could go into a lot of detail on it, but the units get added back in 1 over bar cubed as the units for this. Before we look at these numbers, just as a reminder, how many significant digits should my final value be to? Remember, it's an exponential. That value goes into the exponent. If you're not sure, just remember, and I'm just going to erase that just so that I have something to write. It's not to 4 because these numbers is the order of magnitude. It is the value after the decimal place that is the value itself. So it's 1. So this number down at the bottom is actually only valid to one significant digit. And realize that most of these thermodynamic calculations are using the best available data. So to getting equilibrium constants to 2 significant digits is a stretch. More than 2, impossible. So 1 significant digit on the equilibrium constant. The other thing that I wanted to tell you about is that if you compare this to the -400 is the threshold, we realize that this reaction is less than -400 kilojoules per mole, so it actually is not in equilibrium. Okay? Despite the fact that we can calculate an equilibrium constant, this reaction actually goes all the way to completion. That reaction ends up going all the way to completion. We can calculate an equilibrium constant, but it's meaningless in that context. So delta G is less than -400 kilojoules per mole. While we can calculate an equilibrium constant, really in terms of equilibria, if K is greater than 10 to the 50, on the order of 10 to the 50, the reaction goes to completion. Similarly, if it's less than 10 to the -50, the reaction doesn't react at all. And that's what I wanted to convey in this context. We are out of time, but if anyone has any questions, will hang out here and answer them. And I greatly appreciate everyone in the first class for their patience in coming to the second class. This will, of course, all be uploaded. Yeah, thanks a lot, everybody. Have a great day. Abigail, if you're dropping off pizza, I'd really appreciate it. And I know some of you have presentations this afternoon. There's presentations starting at 3. Show up. Caitlin, there isn't going to be any more problem set quizzes, only because I don't have access to Hayden McNeil. You don't have access to Hayden McNeil anymore. So this is on your onus to learn the material. I will be giving the answers to the questions, but there won't be any more quizzes. Do you have to submit your PowerPoints for the projects? No, you do not, unless I may ask for you to submit your PowerPoint presentation, and that's only in the context that, hey, I found something really interesting in it, and I just wanted to, look at it, do some more, that type of idea. So, yeah. Good deal. I'm going to turn off the recording, and I'll be hanging